Hi, everybody. It's noon, so welcome to Physics 4B, basically. Today is Monday, March 8th. I was thinking February. Anyway, we are March 8th, and today we're still tackling with the third chapter of this class, which is chapter 23. Milo had a great question that you guys need to really think about when you're looking at this one. I know for the benefits for the couple who came late, and also for those who are watching the class basically recorded afterwards. In that, how useful basically are, or comparison between the problems we do in class and the problems of mastering physics. Mastering physics, as I said before, they tackle specific idea, usually 1 to 2 points, okay, at a time, okay? Whereas the things we do in class, they actually, I mean, I have a freedom to go around them and discuss so many things. And actually, most of the times also we discuss several points in the same problem. You will need both of them for the exam, okay, to really expect to really pass this class with flying colors. You have to do all of these problems and understand their in and outs, basically. You have to really be comfortable with them. If, as I said before in the past, and I'm really inviting you several times to do that, if for some reason something is fuzzy or not clear, please let me know. I tend to be verbose in my analysis, and at times it may be tiring or too much, okay? I do that because I want to make sure that every single step in the analysis is clear, okay? Every single step in the solution of the problems is clear. I don't want to leave anything for maybe later on it becomes an issue, okay? So please let me know. Again, if you find it tiring, just basically go back through the problem, pause it, and or go speed up through it, or whatever you want to do to, if you feel comfortable with that idea, and move on. Here is the deal. Once the problem is solved, you really need to do it on your own, and you have to sit back and look at it again. Does it make sense, all of the steps for you? If it does, then you're in good shape, okay? If it doesn't, and you cannot recall the steps, that is a problem. As an extension of those problems, I always connect it to other problems that we don't do in class. So try to start the other problems. Try to do them, okay, on your own. And then see how far you can go in the steps. Go back to the one that we did together and see where it stands, which stage you are in, what you need to do to move to the next step, okay? There is no harm in actually looking at resources. I know that Shag exists and all kinds of resources out there. So if you really want to use those, that's fine for you, okay? As long as you know how the ideas work, how the problems basically progress so that you can solve problems, okay? So this is an extension to the question that Milo has asked, but hopefully everybody is really on board when it comes to that. Now, we can discuss lecture all the time if you want to, but lecture by itself without application sometimes tend to be abstract, okay? But once we do problems, the idea that we were struggling with, it makes more sense that way. Case in point, chapter 23 itself is really a dry idea. I know it's really, it deals with this electric field deriving off of potential, and what is that supposed to mean in terms of practice? Just give me. So for that, I'm asking you guys to look at problem 76, okay? That is a practical way of doing things. It gives you a potential, you want to find the electric field off of it. So tell me the steps, basically. Once you know the steps, you can go back and think of those, if you wish, not really philosophical, but really deep physical ideas that drive those things behind it. Because down the road, it's going to be powerful things. I know you did this stuff, at least for the potential, you did it in Physics 4A. And you're seeing it now. As a matter of fact, you're gonna see versions of it down the road too. So it's really not a, okay. Any other question before we go back into chapter 23? I'm hoping to finish chapter 23 today, and by Wednesday we will go through the examples. I'm hoping actually, hopefully, to get to some of the problem 76 today, if we can, okay? Yes? Sounds good?
Yep.
Okay, so let's get into my notes. First of all, make sure I have the right notes. Good. So let me share chapter 23. Okay. As I said before, the argument basically is trying to find where the electric field derives off of. I think we found the energy, and the energy is basically of how to assemble many points in here, many charges together. And it's just basically the force times displacement, okay? But integrated through all of these particles. This is basically the energy. And I made a big fuss over that factor 1/2, because if you don't include it in the formula for the energy, you really are double counting. So you have to be careful in there. And then we came up with this assignment. There was somebody, I don't know if it's from your class or another class, asked about an assignment that appeared and disappeared quickly. Ignore that, because that's in the past. I used to assign it. But we already went through this assignment, basically through this example. You can come up with whatever example you want to, and it's always there. In class, we used to play a game when it comes to this point, either for Physics 4A when I was doing it, or for this class, where we try to come up with a generic force. It doesn't matter which force it is. And then see if we can find if it derives from a potential. And the force for 1D, it may be easy. It's actually easy. Always finding the antiderivative is easy, as long as it doesn't involve the velocity. Because if it involves the velocity, it's a friction or something. That is friction. Actually, friction depends on the velocity. So that's a non-conservative forces. But if a force depends on a single variable x, you can always think that you can find its antiderivative, and you're in business, so you can find its potential. But when you are in 2D, worst case, actually worse than that, actually, if you are in 3D, just stick to the 2D thing. Almost every single force you come up with, you can think of, and we can invent any forces. And actually, we do it at random. We play this game in class when I was doing this, and all the forces turn out to be non-conservative. We cannot find for them an antiderivative, although they depend only on position. They depend only on x and y. But trying to find their antiderivative, trying to find that their work does not depend on the path. You calculate the work through path 1 and through path 2, and both of them will be different numbers. So the work depends on the path, hence they are not conservative forces. So it takes a special class of forces, really, that derive off of potential when you are in more than one-dimensional problem, like the case, for example, for the electrostatic force. We were lucky, in a sense, when we were doing Physics 4A, that we dealt first of all a one-dimensional problem when it comes to the spring, and we were able to find its antiderivative, which is 1/kx squared. That's the energy, potential energy for the spring. We were extremely lucky in that case that the gravitational potential energy, or gravitational force, was actually deriving off of gravitational potential energy, because the antiderivative of 1/r, basically, when we take it from xyz to the formula for Newton, to find that actually that too derives from a potential. This one also, we're lucky with it because it has also 1/r squared in it. And taking the derivative of the antiderivative of 1/r squared, that's simply 1/r. That too, this too is conservative forces. So nature seems to have favored this kind of forces, although mathematically, the non-conservative forces should really exist everywhere, and they don't need friction. They don't need engines. They can exist on their own, just if you have a mathematical force. Any mathematical force, as a matter of fact, that you randomly chose is going to be non-conservative, which is really kind of and that's a mathematical thing. But yet in physics, we were lucky enough to be provided with these forces. Turns out that all the forces that we deal with in physics are conservative, except those that we know are non-conservative. So here is a distinction between math and physics, okay? Anyway, so we were at a point to find the fact that the electric field derives from potential. And I think we found this potential to be this expression. This is the sum of the potentials, okay? So because we're summing over the charge in this case. So we found it at some point to be, let's go through the derivation again. It's no big deal, okay? So here is the argument. We said the force, the electrostatic force, it has to be the key word in here, static. Meaning, when you bring the charges together, you better fix them before you do anything else. So every charge you bring, you can nail with it too, and nail it to where you put it. So actually bring a hammer and a nail and put it in that place. So that is what electrostatic force means, that things are not in motion, because when things start to move, we have a problem. We cannot really account for this force. So the electric field has set a long time ago. You will see later on there is another thing that comes into play, which is the magnetic field. And the magnetic field has to do with motion, but even then, there is a connection between the two. And this, especially the magnetic field, I know. I'm trying to get some magnets in here. I have them all stuck into my ear. Okay, here's two magnets. You bring them together and they attract, okay? And this is a force, a magnetic force that we can, if I reverse the polarity on them, they don't. No matter how I try, they don't. But if I put them aside, they will attract to one another. And we will find the magnetic force down the road has to do apparently with motion. But that magnetic force turned out to be not a vector, okay? It acts like a vector. It has magnitude, it has direction, but it is not a vector. It is what is called a pseudo-vector, almost like a vector. But the electrostatic force now is a vector. So this one is fine. So the electric field in this case is actually, maybe this one also may be a problem. So let's leave the discussion vectors for later on. Anyway, so here is the deal. Can we find a potential energy so that this basically is a gradient of some potential? And if we do find it, then we're fine. We have a scalar function in here that if I'm studying F equals to ma, for example, I can say that the kinetic energy plus the potential energy is equal to the mechanical energy of the system. So that's the deal. And you need the minus for this plus. If you don't have a minus and you deal just with the antiderivative, it's going to be a minus there. So that is for cosmetic reasons. And I know this discussion probably, or at least should have happened in physics 4A. If we did not have it, we can discuss this later on, why the minus there is needed. And it's needed just for beautification, to make things look nice, to make things look symmetrical, that's all, okay? So that is basically, if we can find this function u, that is the deal. So instead of answering this question, we are saying in here, how about if E itself derives of a potential, okay? If I can find E deriving of a potential, I used the letter grad earlier, grad of V, then I can say that this potential, the potential energy now, is simply QV, okay? Because you can clearly see, since the force is QE, all I have to do is just multiply the electrical potential V. So this is the electrical potential. Since I'm saying the force itself is related to the electric field E. In other words, this derives of V, this derives of U, okay? This derives of the electrical potential V, this derives of the electrical field E, U. And there is this Q in here, which is just a scalar, a number. It has nothing to do with anything. It's not moving. Has no position, no nothing in it. So that is the deal, okay? Obviously, the units, I have to fix them. Here for the electric field, we say it's the units of a force divided by Coulomb. So E has the units of Newton per Coulomb. If I multiply it by Coulomb, I'm back into Newton. The units for the voltage, though, for the potential now, is going to be what is known as volt. Okay, it's related to the electric field in here. So it's going to be the units of the electric field, which is in Newton over Coulomb. And don't forget that when you take a derivative with respect to space, so you have to multiply by meter in here. So it's going to be Newton meter per Coulomb. Okay, and we got sick and tired of calling it Newton meter per Coulomb. We gave it a name, which is volts. Okay, this is exactly volts. Sometimes I write things and I don't mean to write. Anyway, so this is what you mean by 120 volts or a 3-volt battery, or that's exactly the same thing, okay? So that is basically what we're getting at. So here is the deal. I'm going to take 1 point charge and find its potential. Once I find the potential for one charge, I'm going to do 2 charges. Once we do 2 charges, we're going to invoke our friend, and that is Anybody remember the name of the friend, our best friend forever in this class?
Superposition.
Great, thank you very much. Have a nice day. That's the one. Okay. So we're going to do 1 point charge, then we're going to do 2 point charges and more. Okay. Invoking the superposition. So all we have to do really is just 1 point charge. And then after that, if it's true for 1 point charge derives of potential, then everything else will derive off of potential for the electrostatic force in this case and the electrostatic field in this case. Okay. So we said that E is equal to minus divergence of V. This can be written alternatively as the integral, because this is the derivative with respect to space. So all I have to do is multiply by dr in this case. This I have a dr in here. So this is actually a scalar in this case, and this is the scalar because this is a vector times a vector dr. Okay. Once I sum up through everything in here, this becomes actually minus dv. Okay, because once I integrate, this is the derivative with respect to space times the space itself. So this is basically like the function d of f with respect to x times dx, and this is exactly the same thing as df, except this is a one-dimensional problem and this is a 3D problem, because this dr itself is made up of 3 vectors. Dr itself is dx, dy, and dz, and this is actually a vector. So I'm writing it in the vector form in here just to show you that this is a d with respect to x of v, d with respect to y of v, and d with respect to z of v. So this is just the compressed version of it. So if I do this dot product, I will have the derivative of v with respect to x times dx. So this is how v changes in the x direction, or at least when x changes. When y changes, it's going to be the derivative with respect to v times y. So we multiply. Remember, the dot product of vector A dotted with the vector B is ax bx plus ay by plus az bz. Again, this is similar. This is the dot product. So there's going to be how the function v changes when x changes, plus how the v changes when y changes, plus how v changes when z changes. So at the end is going to tell me how the function v changes where. What is that vector in here? That doesn't mean anything. I'm sorry. There is no vector in here. It's a scalar. Sometimes, so all of this doesn't exist. Sorry. Okay. So it's just a scalar function, okay? That's the whole point of the whole exercise, is not to deal with vectors anymore. Okay, so that means that if I integrate both sides, I'm going to find v equal to minus the integral of EDR. That's it, okay? And this is an indefinite integral, so don't forget that constant. So in other words, the potential, the electrical potential is going to be defined within a constant. Just like the potential energy also was defined within a constant. So where you choose the height as being equal to 0, where the potential is 0, is of your choosing. That's a constant, okay? Usually, sometimes it's stated in the problem, sometimes you change it, you choose it yourself, because what matters really is the difference in potential. It's not the potential itself. So when they tell you you have a voltage of 120 volts, what they mean is you have 2 nodes where the plug can go in. The difference between the 2 is 120 volts. It's not like one of them is 0 and the other one is 120. So one of them could be 73 and the other one is 120 plus 73. So it's always that. And then furthermore, actually for the current at home, it's an AC current. So it's changing, okay? So it's not fixed. So sometimes one of them is higher, the other one is higher. So what matters really is the difference of potential in here, and we'll see that, okay? Okay. So if we have to do this integral, remember E for a point charge looks like this. E is equal to Q over 4 pi epsilon naught times R hat over R squared. This is for a point charge, okay? And dr could be in 2D at least, is the change in the radius times the radial direction in the radial direction. So in other words, I have an r vector in here, okay? Which way can I change the r vector? I can add to its length by an amount dr in the radial direction, and also I can rotate it by an angle d theta in the theta hat direction. So this is the theta hat direction, this is the r hat direction. The arc displacement in here is equal to the radius, as long as I fix the radius, okay? The radius r times d theta times this angle in here, d theta. It doesn't matter when I do the, so plus, if you wish, r d theta times theta hat. So when I do the product of r hat from the vector e, here, E has an r hat. dr has at least two components in 2D. It has one in the r hat direction and another one in the angular direction theta hat. In the 3D, actually, it has another angle which is perpendicular to both of them. It's still in another angle phi hat. It's still the only thing that we're going to pick when we do the dot product is this dr from this r hat and E itself. So it doesn't matter. The other angular directions don't matter at all. So the integral at the end of the day will be, for the potential for a point charge, is going to be minus the integral of q over 4 pi epsilon naught times dr over r squared. And clearly, this is just the integral of negative 1 over r squared is just positive 1 over r. So it's going to be q over 4 pi epsilon naught times 1 over r plus a constant. If I can choose the constant to be 0 when we are far away from the charge, then that constant is 0, because when I plug in r infinity, this term goes to 0, and this term is 0 by choice of the origin of the potential, then this constant is 0, okay? So indeed, the electric field derives of a point charge derives of this potential, okay? If you ask, how about another charge, then put another charge Q2 in here, and just using the superposition, you're in business, okay? So this is basically how the electric field derives of a potential. Since the electric field derives of a potential, then the electrostatic force derives of a potential, which means that it's a conservative force. So the electrostatic force F, which can be written as minus Q, the grad of V, is a conservative force. That means that I can find the potential that is associated with it, which is U is equal to QV, is conservative, meaning that if I add this one to the stuff that we did before, we're in business. By the way, the units in here, again, very important. The units for the potential energy is like any other energy, is in joule. And the units for the voltage, which is actually a joule, divided by Coulomb. And Coulomb is really not a fundamental unit. Joule is not actually a fundamental unit too. It's a Newton meter. When Newton is not a fundamental unit, it's a kilogram meter per second squared. And Coulomb has to do with the ampere, which is a fundamental unit in the MKSA system, where meter, kilogram, second, and an ampere. Okay, so we're going to define the currents shortly in the next few chapters. And we will get rid of this Coulomb in here because it's not really a fundamental unit, but rather it's a derived unit. It has to do with how many amperes pass per second, okay? So that's basically, and the ampere and second are both fundamental in this case. So again, this is in honor of Mr. Volta, we call the volts. Okay, so that's the units of the voltage. From this point on, from now on, because remember, the electric field can be written as minus grad of V. From here, I can take the units again of the electric field as being that of a volt, the unit of the voltage, over the times the units of the derivative with respect to space, which is actually 1 over meter. So actually, this is volt over meter. From this point on, you have the choice. Most of the times, you're going to be seeing volt over meter for the units of the electric field instead of a Newton per Coulomb, okay? Which are the same thing, by the way. Newton per Coulomb is the same as a volt per meter, but the volt is a common unit used for a lot of applications. So from this point on, and the discussions, you're going to be calling the electric field, the proper unit for the electric field is volts per meter. Make sense? use these units. I think you might get problems wrong if you do the wrong units from this point on. I think in mastering physics, because it's looking for this volt per meter, not Newton per Coulomb. Make sense, everybody? This is item 1 of the day, to remember this unit for the electric field. Good?
Yep.
Okay. Let's do some stuff with these things, okay? Let's take a plate that has distribution of a charge sigma. So this is a plate that has an area A big. Okay, this is the area. And underneath of it, I'm going to put another charge distribution minus sigma. So sigma is the same. Sigma is charge per unit area on the plates. Except I was very careful in here to make sure that these two plates basically have the exact same distribution of charge. In other words, if I have two metals, for example, take an electron from here and put it in here. So this one will be positively charged, this one will be negatively charged. Take another electron and do it, okay? Keep on doing this until you're said and done with it, okay? And I want to find, first of all, the electric field between the two regions, and then the potential energy or the electrical potential in between them. That is what I'm trying to find in here, okay? First of all, the electric field. Do you guys remember when we did the plate a long time ago using Gauss's law, that this one creates an electric field in any region on this side? It has the same magnitude, sigma over 2 epsilon naught. And it's pointing away from it always whenever you are a sigma over 2 epsilon naught, correct? You guys remember this? When we did the plates. Here, the results in blue. You guys remember this discussion we had a long time ago for the plates, and we argued here and there using Gauss's law? Yes or no? Okay, at least some people are writing in the chat. Okay, very good. Thank you very much, Jason. Okay, if it's a negative charge distribution, it's the same formula, except I have to put, instead of positive, I have to put negative, that's all. So this one actually is going to be pointing in here. This one is going to be pointing in here. This one is going to be pointing towards it. And this one is going to be pointing towards it. And it's going to be pointing towards it with the same way because it's a negative charge. The magnitude is going to still be the same, sigma over 2 epsilon naught. Except for negative charge, the electric field points towards it. For a positive charge, it points away from it. But the magnitude is the same because the plate is infinite. It's a big plate. Okay, do you guys remember that now? Good. If not, I suggest that. Very good. Thank you, Monserrat. Okay, so here is the deal. Outside of this plate, I have two arrows. One of them is pointing down, the other one is pointing up. Both of them have the same magnitude, sigma over epsilon 2 epsilon naught. How much electric field do I have outside and below the negative plate if I add them up? How much should I have? One of them is going up, sigma over 2 epsilon naught, and the other one is coming down, sigma over 2 epsilon naught. The blue is going down, and the red is going up. How much do I have then if I add these two vectors? Thank you very much, Jason. A big fat zero. You wrote it too small there. I know you can do bigger than that, but that's exactly how much electric field I have on below. I'm going to look at above the positive plate. I have the blue pointing upward, and the red pointing downward, and both of them are actually sigma over epsilon naught too in magnitude. So this 2 is sigma over 2 epsilon naught, okay? So how much total do I have now? Also above the positive plate. One of them is pointing up, the blue is pointing up, the red is pointing down, the magnitude is identical, sigma over 2 epsilon naught. So I have you can say it, I know you know it. Come on, guys, don't be shy, okay? Shyness is really one of the problems for physicists, or engineers for that matter. Thank you very much, Jason. Okay, very much, good. So we have a big fat 0, 2 up there in here, okay? Here is the trouble though, the region between the plates. The red is pointing towards the red, which is down. The blue is pointing away from the blue, and it's down. Each one of them is sigma over 2 epsilon naught. So how much do I have in between the plates? Now it's not 0. It's going to be.
It'll just be sigma epsilon naught, right?
Yeah, the 2 cancels because you have basically 2 of halves. So between the plates, we have an electric field that is not 0. So this is E, by the way. And outside of the plates, we don't have any electric field. So if I have 2 plates, and I was careful enough to work them so that the charge distribution is the same on both plates, except one of them is positive and the other one is negative, all I have to do is borrow from one and put the other one. So that's what ensured that thing. What happened in this case, if they're large enough, if they're not large enough, just make the spacing between them as small as possible compared to their size. Then in this case, there is no electric field outside, and inside it doubles in magnitude. So what this device is, it traps the electric field. This device traps the electric field. Do you know what this device is called? Does anyone know? Where the electric field is non-zero between the plates, and it's actually 0 outside of the plates. Anybody knows?
The capacitor.
That is exactly what it is. It's a capacitor. So this is a capacitor. That's used actually to do, among other things, is to store energy, because if I have an electric field, then here I have V, which I multiplied by Q. Therefore, I have actually energy in this region. So it's a useful device. So it's a device to store energy. So let me redraw this device in here. Now it's full glory. So this is the positive plate. This is the negative plate. Don't forget that there is a sigma over 2 epsilon naught. The electric field always points from positive to negative. And its magnitude inside is constant, equal to sigma over epsilon naught, okay? Outside is 0, here is 0, and here is 0. Inside, it's this number. So if I'm curious enough trying to find how much potential I have, all I have to do is choose, for example, this is the origin of the axis. So this is the y direction, okay? This is the height, moving from low to negative. This distance is d, by the way, so I'm going to assume that distance between the 2 plates is d. Oh, man. So this distance is d. The plates have cross-section A. So this is a cross-section, I'm not drawing that cross-section because it's going all the way inside the screen, okay? It's going all the way to the other side. I can't draw it, okay? Otherwise, I have to tilt it a little bit and show you how about A big. A must be very big. At least its square root must be very big compared to D for this thing to work. Otherwise, we have problems at the edges. So we really need to be somewhere in the middle where this distance is big in here. So let's find that potential. Again, if I do this, dx and dy are dx and dz are equal to 0. The only thing that remains in this dot product for dr is simply in the r hat and the y hat direction, which is ij hat. So everything is gone. So the electric field is constant. So if I do the dot, and the electric field is pointing in the negative direction, by the way, I took j hat this way. So the electric field, if I want to write it as a vector in this notation, is clearly equal to minus sigma over epsilon naught times j hat. That's by choice of this coordinate system. If I point it in the opposite direction, then we have different signs in here. So the electric field is this way. So the potential is going to be the integral, the entire integral in general of E as a vector times dr as a vector. E and dr, they're in the same j hat direction, except one of them is constant in magnitude because it doesn't change with y. So I'm going to pull it outside of the magnitude. So it's going to be minus sigma over epsilon naught. And the only thing I'm left with is the integral of dy. And we know what that is. That is actually y. The integral of dy is just a y. That's it. It's like integrating, for example, for mg. Remember when we were doing mg when you guys did mg? It's minus mg. And at least it's mg pointing down, okay? Because the weight is pointing down, displacement is up. So when you do the force again, it's going to be minus mg times dy, and you integrate to find the potential energy is just mgh. Mass times gravity times height. This looks identical to it. As a matter of fact, the similarities are very, very close from it. As a matter of fact, the potential in here, when you integrate this dy, is going to be equal to minus sigma over epsilon naught times y plus a constant, because this is just the entire derivative for it. So this looks like it's an easy problem for us to do. And how do I choose this constant? I could choose it in such a way by saying the potential is equal to 0 in the lower plate. If that's the case, then all I care about is the potential anywhere in here as a function of y, okay? So if that's the case, then obviously outside, and I did not do that, outside, if I integrate v in this case, it's going to be constant, okay? So integral of 0 dy is going to be just a constant. And I can choose this, since I chose v equal to 0 in here, by continuity, this entire region has a v equal to 0. So if I choose the entire region below to be 0, then I have to be careful in here. The potential may not be 0 in this case. As a matter of fact, it's going to be something finite. And let's find it, okay? So we found the potential to be then V equals to minus sigma over epsilon naught times y between the plates. If I were to draw this as a function of y, the minute I move a certain y from the lower plate, the potential is going to be the same. So I'm going to use this blue thing in here to indicate that if I move, let's say, for example, a meter away, this is too much for a problem, okay? So fraction of a millimeter away from the lower plates, the potential is going to be the same because it depends only on the height. Why? How far I am from the lower plate, okay? So this potential is going to be a number. And then as I move higher and higher, the potential will increase, of course, in magnitude. Did I do this right or wrong? Hold on. There is another minus that I forgot to include in here. There is actually a minus in the formula itself, so this is wrong. Remember, the formula itself has a minus in it because E is equal to minus grad, and the E times dr is a negative, so this number is a positive. So that's why I was getting some nonsense in here. It should be increasing as we move away from the negative plate with height, just like the potential mgh in here too increases with height. If you put the mass at a higher height, it's going to drop because it gained potential energy. This is very similar to it. So if I put a positive charge in here, 1 coulomb in here, that 1 coulomb will drop. Just like the same thing, if you put a mass in there, it's going to drop. So again, if I continue with another height that is higher than the first two, the potential will increase, okay? Because it's a linear function with height, that's all. That means if I go equidistance in here, I will get the potential increasing by the same amount. So this is the line until I reach the top in here, in which case the potential will become at the upper plate. The potential is going to be equal to exactly sigma over epsilon naught times the the separation D, because Y is reached D. Now, anywhere in here, it has to stay the same constant because of the fact that the electric field is 0, which means the integral of 0 is constant, and that constant is equal to the value here. So the potential in here doesn't change in this entire region. So it's going to stay sigma over epsilon naught times D. So that is basically an experiment we used to do in the lab, where you have conducting paper and you come up with basically lines of conducting materials on a plate, and then you connect it to a power source, and you connect your meter in this case and start finding the potential going from one line to the other, and you trace these exact same lines in here and where the potential is the same in here, okay? And that is basically how you track your potential. Now, here is a key idea in here that we're going to get to it very, very quickly. First of all, before we do that, as I said, if you put a positive charge, if you put 1 coulomb in here, it's going to be attracted to the negative plate and repelled from the positive plate, and it's going to fall. And it's going to fall with an acceleration given by basically this value of the electric field times the charge Q, okay? Because remember, the force is still equal to QE, and Q times sigma over epsilon naught, that is basically the force. This of a charge that you put in there, let's say, for example, it has mass m, so its acceleration is constant, which is Q sigma over epsilon naught divided by m. So it's just like gravity, except now this is the acceleration with which this particle will accelerate toward the negative plate. This is not then the whole thing. Sometimes you put an electron in here. If you put a negative charge in here, well, it's not going to fall down, it's going to fall up. So if you bring a charge in here and you put it in the same place in here, well, this charge is not going to fall down, it's going to accelerate with the same acceleration, actually, if it has the same charge and the same mass, because the charge and the mass depend on that, and it's going to accelerate toward the positive plate. Okay, so this is something we don't see in gravity. Gravity, everything falls down, whereas in this case, you can have positive charges and negative charges. Positive charges behave like masses, they fall down, except electrons, they don't have, or negative charges, they don't have counterparts in that case because they will fall to the ceiling, okay? So that's basically how this is. I mean, if we had negative masses, they will accelerate according to the same gravity to the ceiling, and you will find all of the negative masses basically stuck on the ceiling, okay? So that's basically how this would work, okay? So that's item 1, okay? The region for the same Y, as you can clearly see, it's the same potential. Let's take an example in here, okay? A lab example, similar to what we do in the lab. If this were 0 potential, 0 volts, because you take the voltmeter and you actually attach the two cases to the two ends for it, and you put it on one side. From there, you changed your reference point. If you put it somewhere else, that becomes your starting point. Okay. If you say, for example, the black end of the voltmeter, which I have one in here at some point, I'm going to put it, not today probably. So, what is my? Oh man, sometimes I lose sight of this thing. Okay. So if you put it in here as being 0, so therefore this will become negative, and that's going to be positive with respect to that point. That's all, okay? So if you put the 0 voltmeter in here, and let's say this is 1 volt, this is 2 volt, this is 3 volt, this is 4 volt, and this is 5 volts. So you have a 5 volt difference between the upper plate and the lower plate. This entire region will stay 5 volts, and this entire region will stay 0 volt, okay? These lines in here that are in blue are so-called equipotential lines. The potential is the same because it only depends on how far you are from the plate. That's all. Okay. The electric field, as you can clearly see from this picture, is perpendicular to the equipotential lines. The electric field is in the y direction. The equipotential lines, they are actually perpendicular to it. Okay. Is this behavior only unique to capacitor, or is it true everywhere? Let's see. Equipotential. What I mean by the equipotential is the potential is the same surfaces, equipotential surfaces. On the surface, the same on the surface. So here is a surface, it doesn't matter which. You go through it as you travel, okay? The potential is the same. So if it was 5 volts in here, it's 5 volts everywhere, okay, on the surface. So it doesn't change. That is by definition what equi means, the same potential. So it's the same potential surface. So I want to know how is the electric field on that equipotential does. I know I saw it just now. It's perpendicular to the equipotential lines. The equipotential line in blue and the electric field is actually on the with this black arrow. So both of them are perpendicular to one another. Is this behavior unique to a capacitor, or is this true all the time? So this is what I want to do. I know the difference in potential is 0. That is basically how we defined it. And the equipotential in here is equal to the negative of EDR between these two surfaces, between the 2 points on the surface. So this is point 1, and this is point 2. So if I take this point in the surface and this point on the surface, both of them have the same voltage. Both of them have 5 volt with respect to some reference. It doesn't matter. So I'm saying there is a point somewhere in space where this is 0 volt. So this point in here is 5 volt with respect to that. And this point in here is also 5 point in here. As a matter of fact, any point on that equisurface, this is not a line. Of course, I'm trying to draw a surface so that you guys see that this is the same thing everywhere. So as long as you are on that surface, this integral must be 0 because there is no difference between the potential on one side and the other. It's the same potential, okay? So that means that this product is 0. The product of the vector E and dr must be 0. Where dr is on the surface. Dr must be on the surface. Okay? If you move from one point to the other on the surface, then in this case, that's what this integration is all about. Then the dot product of these two vectors is 0. That means that E is perpendicular to any vector, actually, dr of finite size, okay, delta r, if you wish, on finite size, on the surface. Hence, the electric field is perpendicular to the surface all the time, because it doesn't matter which 2 points you choose. I choose 2 points very close from one another, but you can choose any points in here, as you can move from point to point to point in between. So the electric field is always perpendicular to the equipotential surface. This is an essential result that I really want you to guys to remember too. Okay, this is item 2 that I want you to put in your own words. This is not just true for the capacitor, it's true all the time. Okay, so that is an important result because this is what allows us to draw the electric field lines in the lab. Because in the lab, we have access to a voltmeter that measures volts, okay? So if I take the voltmeter and I'm very careful to trace, if I find, for example, 5 volt, I want to find the next 5 volt, and I move around that point until I find 5 volt. Then it's easy. I mark the first point and the second point. Now, I go around also with the voltmeter until I find the next 5 volt. What I'm drawing in this case, I'm drawing a surface that has 5 volts. So I have drawn an equipotential. I know the electric field must be perpendicular to every single one of those points. So if I connect them all, the tangent basically to it, then I know where the electric field is pointing in that region. Move away from it slightly, then I find the 6 volt, for example, point. That is actually, and move around the charges to find the 6 volt surface. Then in this case, I have found the electric field that is perpendicular to the 5 volt and the 6 volt, and I can work my way all the way through the entire space, basically. So this is a technique with which we use in the laboratory to find the electric field, at least direction, and even magnitude. Because remember, the electric field is actually used as a gradient of the potential. The electric field is actually used as a gradient of the potential. So if I move from 5 volt to 6 volt, and I find that I need very little space for it where this occurs. So I have a high gradient. But if I find the separation between the two is very large, this means I have a low gradient. The electric field is kind of weak. It doesn't change much between the 5 volt and the 6 volt. Whereas if I have a small space. So finding the equipotentials is key to finding the electric field. So this is that's why the unit now has changed. That was item 1 of the discussion. The importance of V, of finding of V, both equipotential surfaces, I'm sorry, and how it changes to find E. So if you are an experimentalist and you care about experiments, this is a very important point for you. Forget about the math, forget about all the problems on how to do gradients and derivatives and partials and all of that nonsense. This is when you go to the laboratory, pull your sleeves and try to find that electric field experimentally. You guys understand the importance of this concept at this point? Yes, no, maybe. Come on, guys. Okay, very good, Jason. Okay, everybody, this is item 2 of the discussion. I really want you to connect the two. The electric field is always perpendicular to the equipotential surfaces. Finding basically the equipotential surfaces will help you find the direction of the electric field, because the direction is easy, okay? How the electric field is growing, that's the opposite direction, okay? So let's say, for example, practical example, I found this surface in here. Where is my pen? Here is my surface. Here is second surface, okay? This is my 5 volt. This is my 6 volt, okay? Obviously, the electric field points in the opposite direction. It's always from high to low, okay? So the electric field, then in this case, I know it's pointing this way. It's perpendicular to this surface. So it's this way, and it's perpendicular to this surface. So probably let's exaggerate this surface a little, okay? So the electric field now line is this way, okay? The separation between these two will tell me about how the electric field is changing with distance. So taking the derivative, if you wish, 5 minus 6 divided by the distance is exactly the electric field. Just like when you take the derivative of the velocity, the distance, displacement 1 minus displacement 2 divided by the time 2 minus time 1, that gives you the velocity. This, though, the voltage at some point minus the voltage initially divided by the how far you are from this one to how far you are from the second one will give you the volt per meter, which is exactly the electric field. So you get a lot of information. You get the equipotential lines to find the direction of the electric field and which way is changing. It's actually the negative. The business in here of that, why the electric field points this way is because of that negative sign, remember? So if this is 5 volt and this is 6 volts, so the electric field is pointing from 6 to 5, okay? And then also the magnitude, which is just the ratio of the two voltages over the distance between the points. If it doesn't change much over long distances, then you hardly have a very weak electric field in this case. But if it changes rapidly, that means you have a very strong electric field in that region, okay? As a matter of fact, if it doesn't change at all, like this case in here for the capacitor, this is V is 0 everywhere. That means 0 electric field. The electric potential in this case is sigma d over epsilon naught. It doesn't change anywhere in here. The electric field is 0. So if it doesn't change and you move around, hover around as much you have, then there is no electric field in that region. The electric field is 0 because the potential is constant. It doesn't change. So that is why the word gradient is used. Gradient is tell you how steep you are. You go on a climb, for example, and it's very, very, very smooth to climb it. That means you have very little gradient. That means if you let a rock in there, it barely starts to roll down because there is not much gradient in the height. So that means the force is very small. That is exactly the purpose of the incline. But if the incline, the gradient is steep, that means that there is a very big acceleration and you fall rapidly in this case because the electric field is strong. Does this analogy make sense to you guys? Okay, very good. The only trouble with that, Montserrat and everybody else, is that don't push this analogy too much, because in the case of electric charges, some of them will fall upward and some of them will fall downward depending on their charge, positive or negative. But the speed with which they fall has to do with this story in here. Okay. I hope this drives the point. This is the heart of the topic. Okay. Using it later on and doing this epsilon stuff, I mean, partials and all of that is just applications of these things. Let me discuss the case of conductors. Again, if I have a conductor, this is a material that is conductor. I know the electric field is 0 inside, which means the potential is constant. Okay. How much constant depends on where you choose the origin. Okay. Then the electric field in here, I mean, is some value. It's not constant, depending on how much charge I sprinkle in here. And this charge will be a sigma charge, because it's going to be on the surface. It cannot be inside. So this is a conductor now. Conductor cannot have bulk charges in it. Okay. Now, the distribution of the charges in here will be in such a way they will be uniform distribution also. Okay. And there cannot be a difference in potential between this point and this point. This point, if it has a V1 voltage, this point V2 must also be equal to V1, because if the difference is not 0, charges will start to move. And we are no longer in electrostatic case, we're in electrodynamics. The whole thing reposes on the idea that charges are not in motion. Where is the word that I used? I think it was way in the beginning before we moved this thing, electrostatic. Okay. So again, remember the plates. If I put a charge in here, it's going to accelerate down. If it's positive, and negative, it's going to accelerate upward. So if there is a difference in potential between the plates in here, this, I mean, not the plates, I'm sorry, in the case of a conductor, on its surface, on its outside, it cannot have a difference in potential anywhere. If it's 5 volts somewhere, it's 5 volts everywhere, because if one of them is 6 volts, charges start to move in such a way to cancel that difference in potential. Okay. So they will not have, because charges will move, and they cannot have that. So the surface of a conductor is an equipotential. Short of saying that, that means charges are in motion. And when they move, they actually will move in such a way. Let's say, for example, you have, so for some reason, charges, oops, what happened in here? Okay, for some reason, a charge on the surface became, one of them is positive and the other one is negative. Now we have a problem. We have an electric field. So the charges will move, the electrons will move actually until they cancel that, until the charge in here will cancel this distribution and that distribution, everybody will be happy. That's the only time when they stop, because they're communal. They don't belong to any specific atom. Okay. Does this make sense, that the surface of a conductor, regardless of how much charge you have on it, is actually an equipotential? Which yield to the second thing, that the electric field must be always normal to the surface of a conductor. Outside, okay? Inside, there is no electric field. I mean, it has to be normal. I drew it not normal. So in every point in here, the electric field has to be normal. So in this case, the electric field is pointing this way, because this area has to be, and this case has to be. So the electric field, as a consequence, the E field is normal to the surface of a conductor. For an insulator, no, an insulator can have whatever you want to. Okay, but conductors have this unique behavior. That's why you use the so-called Faraday cage, because you can sit inside and actually the conductor will protect you. So if you somehow run into a storm where there is a lot of discharge from the air due to a storm, you can sit in your car, and your car, if it's made up of metals, you should be fine, because those charges, when they hit, they were going to go through the conductor, the outside surface, and they're not going to reach you inside. Okay, so this is the same principle behind it too. Okay, the potential inside is 0. Okay, makes sense to everybody so far? So good? Okay, very good. So you have 2 items of discussion. I want to pick up problem 76 because I think we're ready for it. And this is probably, I think, maybe, I'm not sure. I think, okay, I'm not saying the exams will, because in the past I tested on problems like 76, okay? That means it has to be taken seriously. So problem 76 from the 15th edition. If you're wondering what it is in the 14th edition, please let me know. I should find it, okay, for you. So here is a problem, basically. It gives you a potential. By the way, in the exercise I mentioned at the beginning, where we play that game and finding forces, and we can never seem to find that they're conservative forces, even the absence of friction or absence of engines and everything else. Okay, no problem, Jason. We do it backward too. We take any random potential. It doesn't matter. The force that derives off of it, of course, is going to be conservative force. Okay, so if you do the problem backward, it's straightforward, and this is exactly one of them. Okay, problem chapter 23. Jason is asking about what is this problem in the 14th edition. Oh, wow, I don't see it. No, it's actually problem 78. Got it? So problem 78 on page 783 from the 14th edition is the same as problem 76 from page 778. Is it the same page? No, 783, the other one. And this one is 778, the page. Okay, so problem 78 and the other one. This one is problem 76. So basically what it says in here, it gives you the potential as a function of y and z. And it tells you that this function is some constant a times x squared minus 3y squared plus z squared. And this is the potential, okay? Where a is some constant. A is constant. Derive an expression for the electric field E at any point in the region. So it's easy. So E is a vector that is given by minus grad of V, which I can write it as minus the derivative of V with respect to X, the derivative of V with respect to Z, Y, and the derivative of V with respect to Z. So that is basically how this vector is. So it's a vector whose X component, EX, is equal to minus the derivative of V with respect to X. So if I take the derivative of V with respect to X, Y is constant, so it's just 0. Z is constant, so its contribution from the derivative is 0. So the only thing I'm left with is 2 times X times A. So this, with a negative sign, of course, minus 2AX. Clear? Easy, isn't it? So this is AX. EX. EY is going to be minus, again, dV with respect to Y. Again, I have a minus in here, so the minus and the minus become a positive. I have 2 times 3, that's 6y, and the other 2 will not contribute because they are constants as far as this derivative is concerned. So it's going to be a positive 6a times y, okay? And then finally, the last derivative will look like exactly like that of the x derivative, except that it has a z in it. So EZ, which has a minus dv with respect to z, is equal to minus, again, 2 times a times z. Is this step Straightforward for everybody? Yes? Okay, very good. So it's easy stuff. I mean, the only thing is that curly thing that looks weird, but it's actually in reality, it's not that hard when you think about it, because just straight derivative except that keeping everything else constant. B, the work by the field when a 1.5 microcoulomb test charge moves from the point of coordinate. So we're doing B now. They tell you specifically that you have Q equal to 1.5 microcoulomb. And that 1.5 microcoulomb test charge moves from a point of coordinate X, Y, Z, 0, 0, and 25 centimeters, or 0.25 meter. Okay, this is the coordinates of the first point, to the origin, and the origin has coordinates X, Y, Z that are 0, 0, 0. That's the origin of the axis. So when we move from here to here, what happened? The work is W in this case, because we're not doing energy, we're doing the actual work, is 6 times 10 to the negative 5 joules, okay? Or if you want to, it's 60 microjoules, okay? So the question is, determine A. Well, we know that the work in this case is going to be Q times the difference in potential. Because the potential in this point is U, and the potential in this point is times the difference in V. So let me write it, be careful with it. It's the difference of potential, okay? The final potential minus the initial potential. So that is the work. That is the potential energy. And the potential energy has to do with this electrical potential by QV, that's all. So that's why I wrote it Q times delta V, because I wrote it in terms of the electrical potential. And in general, the work is just the difference in potential in the actual potential energy. So in this case, the work is going to be simply equal to, remember, Q is 1.5 microcoulomb times the potential at the end, which is A times 0 squared minus 3 0 squared plus 0 squared, because all of the points at the end points are 0, 0, 0. So the potential is 0 minus the potential to begin with, okay? Did I forget to put a minus correctly in here? The work has a minus sign in it, I'm sorry. Okay, and remember the work itself is force times displacement. Okay, and the force is equal to minus du dr, minus grad of du. So there was a minus in here that I forgot to include. So there is another minus in here. So this stuff is from physics 4A, okay? So the work is actually minus the change in potential, minus the final, minus initial, because it moved clearly from this point to this point. So minus A times 0 squared minus, is it 2 or 3? Minus 3. 3 times z squared times y squared, which is 0 squared, plus 0.25 squared, 0.25 squared. This is the only term that is non-zero. So basically, at the end, this work is 60 microjoules is equal to negative times negative, that's positive, 1.5 microcoulomb times A times this number in here, which is 0.25 squared. From here, we can solve for the micro and the micro. That's why I actually converted, so they cancel. The 10 to the negative 6 and 10 to the negative 6 cancel. And at the end, the parameter A is just 60 divided by 1.5 times 0.25 squared. 60 divided by 1.5 is what, 40? Because 6 divided by 1.5 is 4. So it's going to be 40 divided by 0.25 squared. And if you multiply this one by 4, and you multiply in here by 4 squared, so 4 times 0.25, that is 1. So at the end, it's going to be 40 times 16. Please verify the numbers for you guys, okay? Please verify this number in here. And the units for it are going to be appropriately, if you are wondering, this is in volts. This is going to be in volts divided by meter squared. So the units is going to be volt per meter squared. Okay, so that's the unit for A. Please check the answer. I mean, the only thing in here is this minus sign, which hopefully you picked it up before I corrected it. Other than that, everything is straightforward in here trying to find A, because they gave you the work and they want you to find that parameter A to make this work. Basically, the final potential energy is 0 and the initial potential is some value in this case. So you subtract the two and you equate it to the work and you find the answer. Make sense? Yes? Yes or no? Or maybe? Okay, very good. Thank you, Aris. Okay. So part C, determine the electric field at the point 0.0.0.25. We should have given it a name, that point in there, because it's famous now. So this point. So we want to find the electric field there. Remember, the electric field, we already found it as a vector in general. It's given by these values. Ex, since x is 0, Ex is 0. Since y is 0, Ey is 0. Since z is 0.25, so it's going to be just this number in there, okay? So Ez, so Ex is equal to Ey is equal to 0. Why? Because these numbers are 0 and that number is 0. So the electric field in that point is going to be minus 2A times 0.25. Minus 2 times A, and A we found it up there. So you guys need to verify A, okay? That's item 3 in here, okay? Always is true. Whenever we do problems, is check the numbers in here and redo the calculation. Verify A, verify the calculation in general. So that is your task. That's item 3. Okay, so you have A, take it from there, plug it in here, and multiply it by 0.25. So it's going to be 0.5 times A. Okay, so it's going to be 20 times 16. Can I get this number? Minus 20 times 16. So it's going to be 320 minus 320 volt per meter, because you have a meter in here, you have more meter per squared in there, and the meter squared cancel the meter in your business, okay? Please verify the sign, because I'm now confused about it, honestly, okay? I need to check that too, okay? Please check the sign while you are at it, okay? So many things so far in the day, so I'm going to clear my head later on and let you know about the sign, okay? Okay. I think the sign is correct now, but check it, okay, nonetheless. Anyway, so we found the electric, show that in every plane parallel to the XZ plane, the equipotential contours are circles. Okay, here's the deal. So we are in question, I don't forget, lost track of it. Question D. So we want to be parallel to XZ plane. If you look at the X, Y, and Z coordinate system, this is XZ plane, and this is the Y. If I move on a given point in Y in here, when Y is constant, those are the planes that are parallel to the XZ plane. So this is one of them, okay? And if I move up and down, they're going to be in this region in here, given by this basically parallel regions, okay? So Y is constant is exactly those planes. Parallel to XZ plane. As you move up and down, basically in Y, you're gonna scan those regions. And V on an equipotential is constant. V is constant on an equipotential. That's by definition what an equipotential means. So that means the V is equal to A, and A we found it somewhere in there, times x squared minus 3 times y squared. This is constant, by the way, too, because this is constant. I can write it y naught, okay? So y is equal to y naught, where y naught is just a fixed number, okay? Plus z squared. And now if I work out this algebra, it's clearly it's going to be a circle, and I can find its radius, as a matter of fact. So this is constant. So it's going to be v over a minus, so it's going to be plus 3y squared naught is equal to x squared plus z squared. This is an equation of a circle of radius. This much, square root of this number is the radius of the circle. So of radius r equal to square root of 3y naught squared plus v over a. Okay? If v is constant and y naught is constant, the radius is constant. So as you move along on that plane, what you're describing actually a circle, and the radius of which is this one. So these are the equipotential regions, if you wish. That's the question they want to. Equipotential contours, in this case, turn out to be just circles. And I can exactly tell what the radius of this circle is. Because x squared plus y squared is equal to a constant. V is constant on an equipotential. A is just that number that we found up there. And 3y naught squared is positive, regardless of where you are, positive or negative. Even if you are below the surfaces, this number is still positive, okay? Because it was negative in here, so when you move it to the other side, it becomes positive. So this is a fixed number that is strictly positive. When you take its square root, you have found the radius of this surface. As a matter of fact, if y naught is very close, is 0, this is actually square root of v over a, okay? Square root of v over a. Okay, the sign is 100% correct, okay? So the sign that we found earlier is correct. Otherwise, we'll get some nonsense if y is equal to 0 and here. Square root of a negative number doesn't exist, okay? Oh man, you're right, you're right. There is another issue with v. V can be positive or negative, okay? So all of the v's need to be greater than or equal to 0 then for the equipotential to make sense. Okay. What is the radius of the circumference contour for v equal to 1200 volts? So V is equal to 1,280 volts, and Y is equal to 2 meters. Basically, find R. You have 3 times 2 squared, which is 4, plus 1,280 divided by that value of A that we found up there, which is 16 times 40. Okay, 16 times 40. I'm going to plug in these numbers and see if I can find some. The radius is going to be in meters, by the way. So let's plug in these numbers. I don't know how we're doing on time. We still have a few minutes. So I have a square root, open parentheses, 3 times 2 squared, which is 4, plus 1,280. I'm not sure about these numbers. Okay, you guys need to make sure that I did them correct. 40 times 16. Close the parentheses of the denominator, close the parentheses of the square root, and hit enter. So apparently the radius R is, so this calculation, 3.74 meters. Again, that's part of the things you're supposed to check anyway. Okay. So this problem makes sense to you guys? Okay, very good. At least makes sense to some people. Please go through it again. Thank you very much, Montserrat. So you guys go through it again, if need be, make sure you understand all the steps. When it comes to equipotential, that means the potential is same. That's why I put V the same in here. I put it as under the square root because it's fixed. It's a fixed amount. In this example, they give you actually 1,280 volts. So basically everywhere on that surface, the voltage is 1,280 volts. It did not change up or down. So if you're tracking it with a voltmeter, anywhere you go there with the voltmeter is going to be 1,280 volt. Granted that you have put the other end, the black end of the voltmeter on the zero. So that number should, the red one should be reading 1,280 volt everywhere on that surface. Okay, so that is basically equipotential. Then also we want it to be parallel to the XZ plane. The XZ plane, that means Y is constant. So that is basically the planes that are parallel to the XZ plane. Okay, I think we're done. I would say probably 99%. So sometimes when I think I'm done, I go back to the lecture and find out an item or two that I will miss. Anyway, we're meeting on Wednesday. We're going to dedicate Wednesday to doing problems. As a promise, problem 41, we'll do that. And problem 41 is to somewhat link to the lecture. So it has symbolism in it, a lot of symbolic manipulations. Problem 77 also, I promise we do that too. And I think to some extent it's similar to this problem, except it has data. Okay. Problem that I tested in it on the past is 72. So probably if we have time, we'll go through it. Problem 61 also is somewhat related to the lecture. And it's related to a different kind of, it's coaxial cable basically. And at some point when we're dealing with capacitors, we will be dealing with finding basically the capacitance. And we're already almost there for this problem. For the parallel plate capacitor that we did, we have all the pieces needed for the capacitor. We have everything needed for it. All we have to do is rearrange that expression that we found for the electric field in the region and the voltage, which is more important, the voltage, which turned out to be sigma over epsilon naught times d. And we're in business. We are in business with this expression. All I have to do is just make sure that Q is over the area is sigma. And now I have the voltage, which is really the voltage difference between the upper plate and the lower plate, because I took the lower plate to be 0, and this is the voltage at the upper plate. So it turns out to be Q over A epsilon naught times d. The inverse of this is actually what we mean by the capacitor, C, okay, capacitance. And so the purpose of the capacitor is actually to store energy. The purpose of the capacitor is to store charge. And that is really the next chapter, okay? But the geometries that are also involved in the next chapter is from problem 61, namely where you have coaxial cables. One of them is that's a certain voltage, the other one had a different voltage, and that is actually a capacitor of a different type. The spherical capacitors, actually, they're also useful, and that is problem 41, as a matter of fact, okay? And so these things have down-road applications when it comes to capacitors, and they have applications in real life too. And actually, I also mentioned when it comes to real life, problem 57. Problem 57 is for the basically salt crystalline structure, which is NaCl. What is it? Sodium chloride. And that too has an importance in terms when it comes to chemistry, in terms of solid state physics, in terms of material science, and a lot of these things to trying to understand them. I mentioned also potentially problem 62 because it has applications in nuclear physics, Geiger counter Mueller, Geiger Mueller counter, okay. And then I mentioned problem 72 since I tested on it in the past. Okay, we'll do our best on Wednesday, and hopefully we'll finish enough materials, okay? Any questions? We have about 1 minute left.
What was the second item of discussion?
Oh man, both items, the second item is a biggie, is the heart of the topic. You remember it now? It's really where the electric field meets the, here. All of this. The electric field is always perpendicular to the equipotential surface, and finding the equipotential surfaces basically allows us to find the electric field direction from high voltage to low voltage, a magnitude, how deep or how steep the descent is from the high voltage to the low voltage, and also being perpendicular to surfaces, meaning I can find its direction. Make sense?
Yes, thank you. Just wanted to clarify.
Okay, to make sure that this is by far the biggest topic that you can take from chapter 23 is the key relationship between V and E, and it helps you in the lab to find E, okay? Because the whole exercise up to this point in here, finding E. Okay, I remember an item that we didn't do in the lecture, which is usually tied to the lecture 2, and that is the electrical dipole. So we need to come back, remind me on Wednesday. First thing first, we do the electrical dipole, and we hit some problems. Okay, it's 1:25. I'll see you guys next Wednesday. And be safe. For those who are sitting in the lab for Physics 4C later on, I'll see you later. Thank you. Bye.
Thank you.
Let me stop the recording. I see you guys. Where is the recording? Here.